Sir, good evening, everyone. My name is CHARIT Chandra Tiwari, and I am currently doing my master's degree in electronics and communication in Sri Mata Vaishno Devi University, Katra. My topic for the project is to simulate virtually doped CNTFET. The objective of the project is to suggest the structure of virtually doped multi-gate carbon nanotube field effect transistor with the help of NANOTUBE white software. The alternative for the silicon to continue with scaling has been worked upon by several groups. The journey has started with basic structures that had progressed a lot in last decade. The CNTFETs are not able to cope up with conventional doping techniques. The doping may result in altering the properties of CNTFET. In this work, a structure is proposed that provides an alternative to doping. The doping is achieved by applying a potential on secondary gates. The properties of secondary gate can alter the source and drain to NP type of materials. And why? So first question comes, why CNT over MOSFET? As we know that in technologies we use processor, we use CMOS as device. Because the MOSFET, according to the Moore's law, that you can scale up to a limit. So, but that limit after a particular nanometers, after 10 nanometers, you cannot go further lower scalings, due to which we come to have, because of the leakage currents and the power dissipation problem. So there are limitations of scaling due to the factors of short channel effect, tunneling effect, oxide thickness, and power consumption. And these are the properties of CNTFET. Like CNT is a rolled sheets of graphene, and its diameter is in the nanometer range. Its electrical property depends on its chirality. A CNT can be metallic or semiconducting depending on its chirality. CNT have high drive current, large transconductance, high temperature resistance suitable to replace silicon as material for the building transistors. Physical structure of CNT carbon nanotube consists of single wall carbon nanotubes or multi-wall carbon nanotubes. And this is the figure of single wall carbon nanotubes having a one layer of graphene. This second slide is of multi-wall carbon nanotube, which consists of two layers of graphene. This is called multi-wall carbon nanotubes. This is a diagram for CNTFET, where we have a source, drain, a gate, and in between them a carbon nanotube is being inscribed. On the basis of the operation, CNTFETs are classified into SB CNTFET and MOS type CNTFET. SB CNTFET is Schottky barrier CNTFET, which works on the principle of direct tunneling principle. But its varied bits is controlled by the gate voltage, and it has strong ambipolar conduction. Now, the MOSFET type CNTFET, it is heavily doped terminals. It provides a longer channel length, and it provides ballistic support in CNTFETs. Parameters that are required for simulations are thickness of oxide layer, gate voltage polarity, dielectric, channel length, ion-off ratios, and subthreshold swings. And the applications of CNTFETs covers like in gas, they are used in gas sensors, Birex detection, used to make SRAMs. And these are the research papers that I go through. First paper is asymmetric, lightly doped Schottky barrier CNTFET in the year 2019. And its results comes out to about the ion-off ratios. The second paper is electrostatically doped tunnel CNTFET models for low power VLSI in the year 2018. And it is of, it describes about the electrostatic dopes tunnel CNTFET device with the reconfigurability. The third paper that I go through covers a design methodology to optimize the device performance in CNTFET in the year 2017. And it is proposed for CNT models is better in terms of power consumption, drain current, intrinsic gain. And why virtual doping CNTFET? Doping CNTFET can alter the properties of CNTFET. Applying voltage on gate is good alternative, and intrinsic field develops inside the carbon nanotubes. These are some of the results that I have simulated. Here, the parameters like 7, 0, 13, 0, and 19, 0 are chiralities. And I have noted out for every parameters, I note two things: ion-off ratio and subthreshold slopes. So this is the effect of thickness of site. This is the effect of gate voltage, polarity. This is the effect of dielectric, which is different layer of thickness of oxide like SiO2, Al2O3, HFO2, and this is the effect of channel length. And on the basis of this, I find a proposed structure that consists of one primary gate and two secondary gate on top and at the bottom of the gate. The gates are being separated by 2 nanometers distance. The length of this gate is 20 nanometers. The thickness of the oxide comes out to the 2 nanometers. And this is the proposed result, which says that the ion-off ratio is 3.14 into 10 to the power 6. The subthreshold swing is 70 millivolt per decade. The length of the channel is 20 nanometers, and the oxide thickness comes out 2 nanometers. I have used NANOTUBE software. It is an open source software which runs on Linux, CentOS, or Ubuntu, and under which we run a Python module files. The conclusion: virtual doping reduces the problem of physical doping. The length of the channel is 20 nanometers. The gap between the gates is kept 2 nanometers, and the thickness of oxide is kept 2 nanometers. These are the differences that I have undergone.
Well,
Thank you, sir.
presentation. I couldn't able to understand like why virtual doping. I mean, uh,
Sir, no, in normally when we dope, when we apply a doping, uh, there is a in VLSI every chip has to go under various processes, and doping is one phenomena. So
okay,
it affects its various parameters like ion-off ratio, subthreshold slope. So in order to better that, we are doing over a gate, primary gate, we applying the voltage. So that the parameters like ion-off ratio, subthreshold slope, DIBL ratios, which are very essential for design, comes out to be as industrial requirement or better results.
okay. It's basically you're doping through software. You're just seeing the
Yes, sir.
result.
Yes, sir. Nanotech, sir.
Okay, fine. Thank you. Good work.